our submission towards the computation, well, it's called computation, but it's for the submission of the Design Core Putt Putt competition, which goes on almost every year. So Design Core is part of a larger umbrella that's called the Detroit Month of Design, which goes on for about a month. And they have a variety of events that they have competitions and people win installations and they participate in these. So this one's the Putt Putt competition. It's based on a 10 by 10 design. You're restricted by a 10 by 10 space, and it has to be installed and taken down within an hour. And you have to launch it at Eastern Market after dark and light up Livernois. So our concept when we first started this was, let's have a design that people can come and play over and over again, that they're not going to get bored of, that it's always a unique experience when you do this. And for order to do that, we leverage computation to do that. Because computation, you can have a large amount of data, and you're able to manage that, and you also use that data to generate designs. So the first thing we did was, with our 10 by 10 space, we divided up into a 5 by 5 grid. So that was able to give us design options, or able to break it up into modules to create these different designs that we can shift around, but also will help us with the portability because we have to take this down and put it back together within an hour. So to use these tools, we use Rhino and Grasshopper, which are visual programmers. So to design with this, it's usually the opposite of how you typically design. So when you typically design, you'll start big and you work your way to the detail. With generative design, you start small and you let it populate big. So we focused on just that 2 by 2 module. So the first thing was the ball, was the curve of the ball, the actual, like, okay, we have the motion of the ball going through. And we defined that by just 3 points. It's a simple 3-point curve. And we overlaid that 3-point curve on a 3 by 3 grid. Well, next, we isolated 4 points within the center of this grid, and we assigned it a value. So when the curve of the ball approaches these points are going to move up vertically. And that's a simple just math ratio of, the distance is y, and we're just going to take the half of y, and that's going to be the vertical. And once we establish those points, it's a simple, we're going to generate a surface from those points. And this is just a simple Grasshopper script that we used. And it's defined by 3 variables, the 3 points that define that curve. And we use that, with that, we generated 8,124 modules. So we actually generated 8,124 modules. We didn't just say we made that those are the options. We actually had the script run through all the options and generated an image, and we just assembled the image in a short video. So what do you do with 8,124 modules? That's the next thing. So what? You generated all these modules. What do you do? Well, we have to start classifying them. We have to start understanding what their potentials and opportunities are. So first we added up all our variables. So point A, B, and C, and we established a domain for each of those. And that within that number and within the domain that falls in, we classified it as a par 5, par 4, par 3. And that's how we were able to start breaking all these modules into something a little more manageable. So then once we had a 10 by 10, we had our 10 by 10 site, and we arranged 5 modules for each one. And of course we had 4 neutral modules because we needed a space where someone could lay the ball and start to actually hit the ball. And of course our 1 module that had the hole in it. And just with all those, we had about 10,155 different design options that someone can come up and use. We also expanded that. Once we selected one of those, 10,000, we had about 12,500 different options where we could actually pick up the panel and rotate it around. So it gave us even more options when a player is using it. And we were selected to be one of the finalists, and it was a big celebration. We were really happy, but at the same time, we have to somehow build this thing. So our first idea was, okay, what if this thing was made up of a series of panels, and we had 3D printed standoffs, and the standoffs were attached to the subsurface, little substrate. We picked 3D printing just because that was the most accessible digital fabrication tool that we had. We were a little nervous with all the unique triangle panels because we're pretty limited access with a CNC machine, and we knew we were going to have some very difficult angles, but we were pretty confident we could find someone to get it lend for a few hours. Another obstacle that we came across was all our different 3D printers. So we had two other designers, me and another designer had our own 3D printer, and then Neumann Smith had two Ultimakers. And all these ran at different software and had different hardware requirements. So it became really difficult to have these things talk to each other, and we essentially had to reformat our duplicator 4S and completely almost rebuild it to make it similar to these other ones. And that was because some of our parts were slightly different. We were about 1/16 of an inch off on a lot of our parts, so it took us a while to kind of make sure everything's producing the same result. And also, we noticed some small minor ones, just how the infills worked, how they created circles for the little drill holes that we were planning. So it was a difficult task, but we were finally able to get them to work, and we started finally to make rapid prototyping. And so these were just a few of our examples. We even had like nuts that friction fitted within each part where we dabbed adhesion. There was parts where we just had a simple drill. We drilled right into the part. We even had little parts that flared out. Now each panel is unique, and each one of these parts are unique. So we could have all these different flare outs, and these flare outs were unique for each one. So it was almost like put together a puzzle, and we thought that could be a really quick way to assemble this thing. So this was our first mock-up panel. It was a simple flat panel. We just wanted to see if the triangles were durable, that the diameter of the standoffs worked, and we were pretty happy with it. I think it got us thinking a lot of different ways we can go about. And now, every time when you add different parts to this, there's a lot more variables that go into this. So when we're dealing with wood, you have to deal with the expansion of wood, with the humidity if it gets wet, how it reacts to the plastic in the wood, how they react. If someone is routing it, if they didn't set up perfectly square, does it have an error to that? What if the 3D printing isn't leveled all the way? There could be an error for that. So every time we had a connection, we had about a 2 to 5% tolerance, which starts to add up on our variables and how complicated the script gets. And this is just a quick blow up of how our updated panels will start to look like. How we start to have these wing connections that fit right into it. We're also going to screw them right down. And there's a lot of parts to these little panels. We're looking at almost 1,200 machine screws and 400 unique 3D prints. So this was us assembling our first mock-up. And of course, anytime when you do one of your first prototypes and mock-ups, it takes a while. And so looking into the hours that we're looking into assembling this thing, it took a long time. And the biggest one was the 3D printing. We were looking at it took us 66 hours just to get this panel printed. And then 64 of those hours was just the print time. And we're looking at a total project of 1,600 hours of printing. So, and that's total hours in a month was 744. So we had to work fast, and luckily we had 4 3D printers. So it took us probably about 3 days to generate a panel, which isn't bad, but it was still any manager who sees that amount of time, there's a lot of risk and liability there because you could be 90% done on a long print and it could fail. And now you'd have to start up. Also, these 3D printers are also working with Neumann Smith. If there's a big job that comes up, that's going to be taken up on time. So there's a big kind of worry mark about that. So at this time, our office was going through an office renovation, and Mod Interiors was helping us out. And we got them on board and started talking to them about ideas, and they actually volunteered to help us. And Mod Interiors has some of the best hardware machines, CNC drill presses that we can. I mean, they have state-of-the-art stuff, and we gave them one of the panels for them to cut. And this thing cut ridiculously fast. When we did our test cuts on our CNC machine, it took us an hour and a half for a panel. It took theirs 15 minutes. And that was not even on the fastest setting. So it was a huge time saver, but we still had a large 3D printer. And I think we were at that point where we were prepping to start 3D printing all these because time was ticking. So after a few conversations with Mod and our hesitation with the 3D printing and just the amount of time, they suggested a different idea of what if we got rid of the 3D printing and we just stacked and laminated a whole bunch of wood and we milled it out. And we thought that was, at first we were like, okay, that kind of gets rid of the 3D printing, and that also generates some of the aesthetic, but also it simplified things so much. And also it created an aesthetic I think that works better for a Putt Putt course. And so I think right off the bat when we looked at the numbers and the parts that it took to assemble this thing, I think we were all really excited about it. And also it simplified all our variables. So instead of all these different connections, all these different parts, it was really just, we were looking at 5 variables. And one of the biggest variables was just the thickness of the wood, because they wanted to stack up. If we had one panel that was 5 3/4, and they were like, and we're using 1-inch Baltic birch plywood, well, we could just modify the script to make it 6 inches, and then they could just stack 6 plywoods on top of each other instead of having all this extra cutting time to get to that 5 3/4. So utilizing computation, making that really helped with the fabrication, also helped how we could communicate and how we could work together and make something that's more efficient. So this is their machine running. And that thing's just blaring through some of and in about 2.5 hours, it generated that. And of course, they put a nice clear coat on it. But it was pretty amazing about the amount of time and hardware that they had that would reduce it. And the great thing was, this was something that we would probably never conceive of because of our limitations with the tools. They had the tools that they could do. We were really, like I said before, 3D printing was our really digital fabrication tool. We were limited with the CNC. With them and teaming up with them, we had all sorts of possibilities we could, because they had the machine and the knowledge to run it. And so we see it reduced our whole time by 95%. And it was a huge time saver. And finally, we started looking at different materials. So MDF, there is an issue with MDF, and this is going to be outside. As MDF has a nice clean finish on top. So when you get rid of that nice clean finish, it's exposed to a lot of humidity. It's going to start to swell. It could start to deform. So to minimize that, they always had to put a clear coat right on top of it right away. But if this was going to be outside, people are going to be walking around on it, stepping on it. The clear coat would start to wear. Then we start to get that exposure again. So Baltic birch was something that because of the aesthetic, and also I think because of some of the durability that it has compared to MDF, we were leaning towards that. So these are actually taken just a few days ago. We're about to, now this isn't finished yet. We're about to launch it very soon. And we're actually receiving it pretty quick here this Friday, but this is just a quick exploded animatic, just how we're going to assemble these panels. We're going to have, of course, our panels, and we're going to have our plywood subfloor, which was going to have CNC holes right into it. So that's when we can move the hole anywhere we want to. They can pick up the panel. Users are able to customize their golf course any way they want to. And of course, we'll have the bumpers that can help contain the ball. And this is what it looks like assembled. So, like I said, I mentioned before, it's not finished yet. It is on its home stretch, as the panels are almost all done. I think we're just putting a clear coat on them now. But I'm going to leave you guys with this, that if you want to see the final result, come see us at Easter Market after dark. It's also the same day at the AIA Awards. And we'll also be at September 28th at Light Up Livernois. And if you can't make all of those, you can always follow us at Neumann Smith, or my own Instagram account, Inference Studios, or just hashtag us at computation. So, thank you guys. Thank you for everything. Yeah. Any questions?
Did you design each one of these panels individually and then try to assemble them together just to see what the outcome would be, or did you look at it as a whole at the same time?
When we had our, first we looked at them. We had the script run through all of them, and we looked at the images and wrote data around. We picked out a few of them that we thought were that had kind of the most range. Some of these were pretty flat, and maybe one or two panels were up and down. So there was also a manual process that we went through on these panels. So it wasn't just like we spat it out and we put it into pars. We actually looked at them and made sure, okay, this one has the most dynamics elements to it.
Did you run golf balls over them yet?
Yeah, we have. And a good thing we did, because our first panels, when it slows down, it does hit one of those cracks, and it just follows that crack along. With the full-on CNC routed ones, I'll be surprised if anyone gets a hole-in-one on that, because it's really difficult. So yeah, we lined up a few of them and hit them around. We actually lined up our two mock-ups and bumped them around. And we're like, yeah.
Did you find with the actual balls that maybe you didn't need quite as much elevation to make things pretty difficult? Or
it's funny, we didn't go too much into making how difficult or how easy we can get it. It was actually just more of us looking at, like, picking out the ones that had the most difference, and we're like, okay, we want something that aesthetically has a lot of range to it, and we didn't look at like how difficult this thing could go. Yeah.
Can I ask why you chose to have these be triangles? Like when I think about my time with the Grasshopper, which isn't much, I know that there's ways to apply spline type effects so that you have smooth surfaces. That would be more like a golf course feel to it.
Yeah, absolutely. No, that's a great question. Yeah, one reason why we didn't pick more of a smooth surface was just the limited of our tools. So when we first got the go ahead to put together this competition, you're always kind of like, the first thing you do is stock take of like, what are the tools I have. And that was the first thing, was like, I don't know if we can do something really smooth. And because if we had the CNC machine earlier, I think that would have been a possibility.
So if you were to go back and do it again sometime, you'd probably explore that opportunity.
Yeah, absolutely. I think it was just that idea of, okay, we knew we had limited access to the CNC machine, but we had unlimited access with 3D printers. Okay, we should probably make this more of a 3D printing one. And making this whole thing out, just with those little standoffs, it was an astronomical amount of time to 3D print, but so making a whole panel out of something like that would be out of our reach, including with 4 3D printers.
Was it like structurally stable to stand on?
Yeah, actually, it was structurally stable to stand. That was the other thing, because some of the pieces go up over 6 inches. And so we were like, well, this is a big panel, and it's a big panel for a 3/4 inch MDF. And so yeah, it does flex. And actually, because of that, we changed some of our connections. So we actually had a few nuts and bolts that we screwed into, and over time those popped. Because the wood would deflect, and over time the glue and the friction fit of the nut would just pop out. So we actually switched to just a drywall screw, and we just drilled it right through the panel and into the 3D standoff. And the nice thing with the 3D standoffs is you can control the amount of infill. So each one has all these different layers built into it, and so when with that drywall screw went in, it caught a lot of those layers, and it was hard to rip up. We found that to be a much more durable option.
So despite how much time you spent on it, you learned to...
Yeah, and that was one hesitation was when we were talking to Mon about that point of departure. Was like, man, we spent a lot of time on figuring out this 3D printing stuff and get it to work. But at the end of the day, we had to like stop and look at the design process. And it was like, we would have not gotten here if it wasn't for all that 3D printing and getting this. So this was just a point of departure, and it's just part of the design process. And we have to honor that and be honest with it, and go with it. Because then at the end of the day, we have to answer, well, why did we pick a design that took 95% more time and it cost us more money to do? So it was like, the aesthetics are different, but I think in the end, it's a much stronger project.
And you did this entirely at Neumann Smith?
Yeah,
with your own employees?
So it was most of the time it was me, Trent Schmidt, and Jason Baker. So we us 3 designers put a lot of time into this, and of course Mod was right along with us too.
I assume you did that in off time, not company hours.
Yeah, it was. I think we were lucky.
Company hours.
No, we were very fortunate that Neumann Smith allowed us to use some of our hours. A lot of it was a lot of the 3D printing stuff when dealt with our personal 3D printers were a lot of late nights on our hours, because that was our products and stuff that we wanted to fix up. But Neumann Smith was really nice to allow us to use these hours and to do it. And we were pretty conscious on making sure not to spend too many hours. And we were also very lucky that Mod was able to donate some hours and help us out. But yeah, they actually, again, there's always hours that sneak up on you that you never anticipated on, and that's one thing is just the level of contingency that you should put on the assembling. Talking to Mod, like the amount of hours just to laminate all these panels together was a lot longer than they were expecting. It sounded like. I think I just got the number of about 37 hours of just laminating these together. And also, I was definitely over on the amount of hours I thought assembling our panels with the 3D printing took a lot longer than I thought, because we designed it so it was like, okay, it's just going to be a puzzle piece. Everything's just going to snap in. But there was a few panels that were very close to each other that had the same pattern, and it was like, well, where does this go? And that threw off everything. And something that we thought was going to take half an hour, 45 minutes to do, ended up taking an hour and a half, sometimes 2 hours. And we actually had to cut out a few things just to make the assembly time faster. Originally, we had we had the screws, we had to countersink them, we had to screw into the nuts and stuff, and it took a lot of extra time. So we just used the drywall screws.
I got one last question for you. This one's a little bit more of a curveball. Does Neumann Smith participate in the construction event?
Yeah, Neumann Smith.
Would you use Rhino to assist in the generation of how to stack those cans?
Yeah, absolutely. Yeah, absolutely. Yeah, Neumann Smith does participate in the CAN instruction, and yeah, Rhino. Anytime you're dealing with multiple, like hundreds of different units or hundreds of the same units, and you're configuring them in a unique way, that's probably the best application for the Grasshopper and Rhino. It's just when you're dealing with that much units and information, it's a lot easier to manage, and you can on the fly change things. And I think that's the thing that saved us, was just on the fly when we were changing parts, tweak, rapid prototyping those standoffs. All we had to do was click a button, and it updated everything. Okay, 3D printed something. All right, the nut isn't really friction fitted on this print. Okay, all right, let's tighten it up on this one. And we were able to just click a variable, bake it, and then send it to the 3D printer.
Yeah, because we were using SketchUp to make our little Mario Kart dude.
Oh yeah.
Yeah. We spent a lot of time on that.
Yeah, that would take a while on that one. Yeah. Yeah, that would. But yeah, it's a great tool. The visual programming is, and it's just, for me, it's just going to be more important down the road. As things are just going to get more advanced, it just seems like it automates things, it calculates, and it just makes things a lot easier when you're dealing with a lot of information. All right. Well, thank you, everyone. Thanks for showing
Thanks,
up.
John.
Thanks.